I'm sorry.
I start.
Okay, start. So, the neural networks, they are very useful, but in science, where we do not have tags for the events, we don't have labels, they can have a potential bias. And if you see, let's be sincere, no? If you have a Monte Carlo like Pythia, Monte Carlo like Herwig, there are many regions of phase space where they disagree in an order of magnitude. One predicts 10 times more of jet than the other, or whatever, I don't know. So they disagree. And what they do, they adjust Pythia in this control region, and they use it in this signal region. Now this is being recorded, I should be. I should, but someone has to say, the king is naked. Okay? Bayesian tools, okay? There is nothing free. We will reduce, we're going to be able to reduce the simulation impact because we will be learning from the data as it comes out at the price of increasing some impact on the modeling. Okay, there is some, we're going to model and that has an impact on our results, a potential bias, but we reduce the simulation impact. So it is another way of doing things. I'm going to try to convince you that there is a huge room for improvement or for potential improvement. So the talk. ABCD method, most experimentalists know about. Maybe theorists a little bit. It's about, it's a method experimentalists use, and I would say that in half of the analysis that you see of Atlas and CMS, or maybe 25%, I don't know, they use the ABCD method. It's like defining a control region, and with the other, estimating how much background there is in your control region. Then I will talk about the Bayesian techniques and how they can improve the ABCD method. Then I'll talk about the die-Higgs production to 4 bottoms in a very toy-level model, of course. And we're going to do some comparison between the ABCD and the Bayesian techniques. And then I will show you how we can improve, usually the B tag. I mean, a general thing that we have to start thinking. When you tag something, you are missing potential improvements. Because when you tag, you are deciding that something from here to there it is, and from here to there it is not. But truly speaking, you have some probability curves, and you are missing all the information contained in the shape of the curve. The shape of the curve contains so much information that doing a tag, it's a crime. Defining a control region and a signal region, it's also a crime. Oh, come on, we know more than adding and subtracting. We know seeing a shape, like analyzing derivatives, all these things. So this is about, I'm going to show you how, instead of B tagging, use the B tagging score curves. Even if you don't know their shape, I'm going to show how you can extract their shape by assuming correlation. You know that your channel has 4B, or 2 bottoms and 2 jets, because from physics you know that you cannot create 1 bottom. You have to create them in pairs. So that's prior knowledge you are injecting. Okay, and nothing, outlook and conclusions. ABCD method, okay. The data-driven methods are great, and they are very useful, and they have to do with do not rely on a Monte Carlo simulation. Nobody would ever claim a discover because your data is 5 sigma from your simulation. So these kind of things like sideband fitting and these kind of things are very useful. And the other very useful is the ABCD method. ABCD method, for those who you haven't heard about it, is like this. You use your prior knowledge to say that signal, you define 2 operators. You use 2 operators, invariant mass, how many bits you have, whatever. You define that your signal is in some region, and then you use the other regions to say, okay, you assume 2 operators that are independent. So you say that A is to B as C is to D. Then, since in A you have signal and background, and in B, C, and D you have only background, you can estimate the amount of background in A. And it is very safe. In some sense, you are only multiplying and subtracting. No? If your hypotheses are correct, it's perfect, it works. Okay. It has some limitation. If you have more than 2 operators, 2 independent operators, you have more than 2 observables, or you have more than one background. Okay, it has some limitation. It is very useful, but it can be improved. Okay, something to notice: you need prior knowledge to define A, B, C, and D, because you need to know that signal is in A. You are using hard cuts. You are using hard assignments. No, using control region and signal region. Come on, we can see them both simultaneously and assume that in simultaneously there is a mixture between signal and all the backgrounds, and because of the properties that you expect, infer how much signal you have. There where we're going. Yeah, signal and background regions, okay? And this has a natural conflicting hypothesis. You want regions to be close enough to have the same distribution, but not to be close, so close so that signal is not present in B or in C. It's okay? So that's a natural conflictive hypothesis, of ABCD method. Now, let me do, this is a paper called Improving ABCD through Bayesian Inference, which is how we can improve this. So, a little about Bayesian Inference in this setup. As you can see, this is a very important theorem. Yeah? But it is used in so many different situations that many times you see something and you do not realize that it's being used, or you don't know how it is being used, the Bayesian inference. In this case, it is like this. You have the data, the LHC data, and you're going to model that data as being sampled from a clever PDF with some parameters. You will infer theta once you see the data by just using these techniques, and then you connect theta to physical parameters of interest. Okay? In LHC, as in many cases of sciences, what you have is what the statistician call mixture models. Means, yeah. P of x here? Sorry?
What does it mean if you switch the order? P of theta are x and P of x are theta. So the first one is the parameters, the second one is the data.
Yeah.
Then when it appears again, you switch where x and theta.
Yeah, that is the whole trick of Bayesian equation, that you can, that this is easy to compute, and this is hard to compute. So if you have, sorry. Oh, you mean like P, like this in the denominator? No. Yeah.
Parameters is a bunch of numbers, right?
Yeah, for instance, the mu, let's think about a normal, no? Parameters would be mu and sigma, for instance, no? Theta, well, yeah, variables, yeah.
Data is what? Thousands of numbers.
Data is thousands of numbers, yeah. 1, 2, 1.5, 6, yeah.
So I understand what P of theta of x means. The probability that the parameter has a certain value, it's the probability that you'll get some data. Is that right?
No, sorry. Probability of x given theta. Let's start by this one. Okay, this one is okay. If you assume a normal, if these are the values, it is the normal of x, y given mu and sigma.
Okay.
A productory, no?
Okay. So you claim there's some kind of,
Okay, and the other is what the distribution probability of mu and sigma given that this has been measured. All right? Because usually you have some data, and you say, okay, mu and sigma, I compute the mean and the sigma, I have the normal. But the truth is that this normal could have also sampled these 3 points. No? Like there are many normals around that could sample these 3 points. All right?
so theta is not the data, so it's a model.
No, x is the
Something you measure.
theta, I mean? Yeah, theta is not something you measure.
So P of x is theta is the probability that the model is correct or something like that?
No, it's the probability of a data given some parameters. It would be exactly this. It's a probability, a number. 10 to the minus 5 if you have 5.
But it's a given model.
It's within a given model, yeah. Yeah, it's within a given model, yes. And probability of x, it's the probability of the data given in that model. The denominator comes by integrating theta up there. Okay. So I don't know what this. Okay. Okay. So, usually in science, you have data, and you are trying to understand something that's going on in your physical process, in your process, that produces some events, that you try to get these events. But when you do whatever class, they're trying to get you have that some events are from signal and some are not. And this is a mixture. This is what a statistician calls mixture model. There is a lot of written about this, okay? Each event is either signal or one of the backgrounds. So the thing is how you create a PDF for this. And let me show you to do this, let me introduce you what is called graphical model, which is a technique of a statistician. They have to create PDFs, probability density function, which are sophisticated in the sense that they are composed by different PDF that affect one to each other. I will explain this now. Huh? But it's just a graphical representation of a PDF that helps you to do a calculation. It's exactly the same as Feynman diagram. By itself, a Feynman diagram is nothing. It just helps you to do a calculation. So it works like this. You have random variables. At each event, you sample one random variable for a multinomial distribution. A multinomial can have a few slots. One is signal, one of the other backgrounds, and it has an outcome. We do not observe that outcome. This is why the circle is empty. But this outcome is going to affect things that we observe. In this case, it will be transfer momentum, missing energy, number of jet, number of B. So, depending on if the event is signal or one in the background, you have different outcomes. These outcomes depends on some distributions. I will talk about this. No? So what I said before, if you have number, think if you can have the shape. No? Instead of number of jet, number B, for example, the B tagging scores. Okay? Because think about that. Tagging, when you tag, you are missing information. No? When you tag a galaxy as high metallicity, just use the metallicity or whatever. No? In anything, don't tag. There are now techniques to use the full curve. So, empty circles are random variables which are sampled and not observed. This is your model of what's going on, right? And filled circles are sampled and you observe. If you repeat this n times, because you have n events, you draw a plateau around, and you have the distribution of these things depends on some other parameters. No? If it is signal, maybe it is normal. If it is background, it's exponential. So you have some K classes, like signal and the backgrounds, that have different distributions of the things you measure. Questions here? No? So it's a way of saying that, but these distributions, you don't know exactly where is the Higgs mass. Actually, it's not in 125 when you measure in BB bar. No? It's slightly shifted, and you don't know exactly which is the width of that normal. You have an idea. Okay, and
that got me a bit confused because I thought these two categories were in the upper empty circle.
Yeah, no.
I think that signal and background were both there and are.
Yeah, they are in both places because this is to decide whether it's signal or background, and this is to decide which is the distribution that will have each observed magnitude.
So it's not different effects. It's
Exactly.
just representing.
Exactly. Yeah. If you have k equal 5 here, you have a multinomial of 5 possibilities here. And actually, when you sample this, in each event, you need to sample a multinomial that have parameters. So these parameters have to be sampled, but only once because you have your data set has a different amount of signal and background 1, background 2, background 3. So that tells you that every time you sample in your model, you model that you sample an event, it has to be sampled with some parameters. And these parameters are 1. The things that are outside this plateau are sampled independently of how many events you have in the data set.
So just for me to understand, so this capital D class,
Yeah.
these are like PT of the
Yeah.
jets, invariant masses, etc. And the Z probably, I would think, is like the form momenta of all the particles that you have in the event.
Is what?
The form momenta of all the particles that you have in the event.
No.
Because these are highly correlated, right?
The one below?
The D, because they're coming from the same thing.
Well, okay, here it's very nice question. In this case, if you don't have arrows between them, okay, for instance, things that are not correlated, no? Invariant masses and PT. Say in die Higgs, no? The PT of the Higgs is something, and the invariant masses of the 2B have nothing to do.
Yeah, but they're coming from the same, I don't know what Z then. What is Z?
C is a number, I mean, you can think of 4 slots, and there is a 1 in only one place. And you have, okay,
And then there are correlations, because the Z is determining the whole thing.
they are conditionally independent. Depending on what, okay, you can choose parameter, if you choose like eta, there are parameters that are correlated. Yeah. The grip is to use one that are not correlated. No? In this case, I'm going to show you which one we use that are not correlated. But if they are correlated, you have to put an arrow between them.
Right.
Okay?
So we assume that they're not correlated.
We assume they are not correlated.
They come from the same
Yes.
number.
Yes.
So they are correlated.
No.
I think the ZN is only something that says this is signal, this is background 1, this is background 2. This is what the ZN is.
Yeah, yeah.
So given exactly, just telling you if it's signal or one of the backgrounds.
But they're, yeah, you know, they're, I mean, if you can choose observables that are not correlated given the class. Given the class. In the whole data set, they're going to be correlated because of the mixture. Okay? So yeah, but this is very good observation because you have to choose here parameters that are not correlated to have a grip that you have less parameters to understand the data. Okay. Okay, and of course you have to put the hyperparameters that control your prior knowledge of which are the fractions you expect, which are the whatever distributions that you expect to have the magnitudes that you're going to measure. I'm going to get to this, but they are not just as in the ABCD method that you need observable 1, observable 2 to be independent. Here you have more observables that are independent. In particular, if you create 4 particles, the 4 invariant masses are independent. And they don't measure always the zero because you have uncertainty, whatever. They are approximately independent. So you model data as being sampled from a PDF. Here, you only measure this, but when you model this, somehow you unfold your system in things that occur that are being sampled, where you can plug your prior knowledge. You have some prior knowledge of how is the distribution of the invariant masses, if they are from signal, or in background, they're usually exponential. And that prior knowledge, you can put it, if you make it to unfold the probabilistic model in different building blocks. And this is one of the reasons why these techniques are so useful, because you have the possibility to plug, you extend, you unfold your probabilistic model so that you can plug your prior knowledge in the exactly variables that you're modeling, it's creating the data. And then, of course, then you use Bayes, no? Given the data, you infer your parameters. Okay? And then comes also the latent variable that you can infer it, which is something very similar to a parameter, just that it is the probability of each event of being of each one of the backgrounds. So you end up inferring that too. Okay? Now, no hard cuts. There is soft assignment all the time because the probability, C gives you a probability of each one of being signal or background. So it's much more clever to have a soft assignment. There are no signal and control regions. And observe that you can have K classes without any problem. And you have prior knowledge of each one of the backgrounds. And you can have as many observables as you want. Not only 2 as in the ABCD. In the ABCD, when you have 3 observables, 3 independent observables, what they do, they slice the 0 observables, and they do many ABCD in different slices. 2024. Okay? And you unfold the data to see the internal structure of the data, and then you can have a control injection of your prior knowledge. If you compare ABC,
Where's
yeah.
the modeling coming in this picture?
Well, this is a very basic modeling of a mixture model. The modeling will be, for instance, here you have the invariant masses, to say something. Your modeling is that a signal of the Higgs, there are two Gaussians whose mu is around 125. If it is background, the four bottoms, you expect them to have the invariant mass, you expect them to have an exponential distribution, and that would be modeled here. Okay, it's not written explicitly.
For instance, you can calculate the differential cross-section for Bayes or whatever by chance. Where does that enter here?
Well, at some point, if you want to connect to a physical parameter, you need a simulation. Okay? Because here you can infer the fraction of signal and background. And if your model is relatively correct, you will infer correct, but you don't have a connection to a physical parameter yet. No?
So this is independent of cross-sections or whatever?
Yeah. Well, it can learn. It's unsupervisedly, almost unsupervisedly learns that because of the correlation on the data, it recognizes that there is one class that has 20% and the other one has 80.
There's no correlation.
Well, yes, no, yeah, there is correlation. As I told you, the correlation arises when you see the data. The idea is that in each, it is very important what you're saying because it's crucial. In each class, there is no correlation. You choose observables that in each class don't have correlation. But when you mixture them, but when you see the whole data, the correlation shows up, and that correlation is what tells you which is the way that the two classes are, so that there's no correlation in each class. No, these guys. It is unbelievable what they can extract.
I have the same problem with Jerry. How do you choose these guys so that there's no correlation? But it seems to me that you can, now you're making a hard cut. When you say, I'll choose two of those blue circles that have no correlation, that's a hard cut. But at the most, you get small correlation between them, and you approximate that to zero, right?
Yes.
Deciding there's no correlation.
Yeah, you approximate that, yeah.
Because there's always some correlation.
Yeah, there's always some correlation. Yeah, there's always a correlation. From here to China, no? A butterfly flies in China.
Okay. Here's my basic question. So this is Bayesian inference, right? It's written there. What are you inferring? You're inferring parameters of the model? Or
Yeah, you're going to infer. You say, for instance, that you say, to be clear, that you have an exponential in the invariant masses of the bottoms for background, and you have a normal for invariant masses. You're going to infer the rate of the exponential. Yeah.
It seems to me that what you're really doing is looking at the data and saying, this data is generated by 3 different distributions, and this is 80% on this distribution, 20% on that second one, and almost nothing on the third one. That's what you really say.
Yes.
And then you call one of these signal and the other two
Yes.
but even that
Well, but you knew that the signal is
without any simulation.
but the signal, you know that has a normal distribution, the invariant masses. So you know that one is signal.
Okay, that's a prior, right?
Yes. That's prior knowledge. That's prior knowledge. How are you not going to use that? Yeah.
Okay. So, But if there are two signals, right? There could be two normal distributions. And
Yeah, then you're missing it.
right? Then
Yeah.
you see 3 different distributions contributed.
Yes.
So, so my question again is that when I work in Bayesian inference, I usually do likelihood Bayesian.
Yeah.
Do you have a likelihood here?
Yes.
So you have a
Well, at some point, when you draw this, there is a technique to write the likelihood, which is the probability of the data given the parameters. That's the likelihood, no? This probability of data, this is the likelihood. So this is a way to visualize the inner structure of the data, and then there are techniques from here to write analytically a likelihood.
Yes, but you are inferring the likelihood from the data.
No, you're not inferring the likelihood. You're writing the likelihood.
But if you write the likelihood, you need the covariance matrix, for instance.
Well, if they have correlation, yes. In that case, yes.
So in your case, the covariance matrix is diagonal.
Yes. In this case, we are choosing observables that have no correlation, just as in the ABCD method. They are approximately I'm going to talk now about the Higgs 2-4 bottom.
Yeah, I think the
Search.
example will make things much more clear.
Okay. Okay. Higgs 2-4 bottom. Okay. At the toy model level. Okay. So this is Higgs 2-4 bottom, and the background comes well. The main background is 4 bottom from QCD, but in this example, to make it more simple, we choose BB charm, and 4 charms as the backgrounds. I'm going to show you why. So this is the Atlas and CMS analysis. And what they do, they take the invariant mass of 2 pairs, and the invariant mass of 2 pairs, the other 2 pairs, they construct this variable, chi-square, and they're going to decide that when they put them when this chi-square is less than 50, is signal region, or more than 50, GB is background region. Take a look. They're reducing 2 dimensions to 1. And in addition, they are doing a haircut. Okay? Now, this is what they do. 25. And the second operator, the ABCD method, is whether you have 3 bottoms or 4 bottoms. Okay? They say signal region, the region A would be less than 25 and 4 bottoms. And they assume in the other BCD there are no region, they do the simple rule of A is to B like C to D. Okay. What we propose is, let's have the B tagging score of the 4 jets, no? And the 2 invariant masses. Of course, the B tagging score distribution is not known. We're going to have an idea, and we're going to play with that game, that we're going to start with the bias priors and show how the correlation can push you to the correct B tagging score distribution. I don't know if that's clear, no? I mean, here. The B tagging score distributions for a jet, of when it is a jet and when it's not, you usually have a score. So, okay, you have a probability. This is much mixed, right? So they calibrate, that curve is not known, but they do a great effort and they calibrate a working point from which they know that you have some contamination and some signal. Okay, but the curve is not exactly known. What I'm going to try to convince you is that even if the curve is not exactly known, if you use some prior knowledge on their approximate shape, the correlation that it is in the events, because this is a toy model, because they are either 4B, 2B or 2C, or 4C. So the tagging score are going to push you to the correct distribution curves.
Wait, but now I have a question. But when we write that chi-square over there,
Yeah.
there is already a previous step where you use the chi-square to actually pair the jets, right? Even if you have 4B jets,
To pair them.
Decide which goes with which.
Yeah, that's a subtle thing that we are working on. Yes. No, yeah, but you are using information. That minimizes chi-square. The minimizes chi.
So it's not that the chi-square comes from heaven. There is a reason for that.
Yeah.
Written there.
But you are still cutting.
We are
And you are reducing dimension from 2 to 1.
correct.
Okay? Good. So from 2 to 6 dimension and the shape of the curve. Okay? We are taking the shape of the curve. Okay? The one here, there, condition. Okay. So this is, of course, a toy model, specially designed to success with our. But we're working, I'm going to show you the later things. No? So we do a little setup, synthetic signal for bottoms, background, BBCC, and CCCC, to show the power of correlation to use the flavor, to get the flavor. No? It is a very important knowledge that events are either 4B, 2B2C, or 4C. Because it means that you have 4 numbers that they are either sampled or 4 from here, or 4 from here, or 2 and 2. And you don't need to know the exact shape of the curve, you're going to infer it. Because you have that knowledge that they are either 4 from here, or 2 and 2. Mm-hmm. So we do a little game with 20,000 events, 1%, half, and 0% of signal. And for the invariant mass of the B, we put a normal or an exponential. This is motivated with the experiments, tal data. And the bit tag, okay, here's the bit tag. The real curves,
So you generate this data
yeah, synthetic.
like Python or something?
No, not even Python, Mathematica, like Python. Not, this is full cheating. But you're going to see now later. So these are the state of the art of the bit tagging distribution scores measured in TT bar, where in TT bar is quite easy to measure things because you have 2B always. So if you have 1B, it is very likely that the other one is B. But you know better than us that these things change when you change off, and these curves change when you change of setup. Instead of using this, the orange and the blue, we're going to use these beta curves as an approximation, okay? And we will start from bias priors, and we're going to see how we can, so we generate the data with the given curves, we start with the bias, and we're going to show you how after inferring, we get the correct, okay? And this is, as I told you, this is important prior knowledge. So this would be the diagram, the graphical model where, okay, P signals, some structure, some random mixture that you don't know which shed is bottom and which is charm. And you have you measure the 2 invariant masses and the 4 scores. And with this, this is once you do the inference, as you can see, if you see around here, you have the true curve, you have the prior, you see the little lines, the thin lines, these are the priors. And after we infer, we get the solid line, which matches quite well the real data. So inference works fine, even though we start with the bias prior. I'm not going to go into the details, but the idea is that we run this model, which is the same with which the data was generated. So that's the big cheat, okay? And that works. Now we can compare how better works than the ABCD. Okay? And of course, the last thing we need to know is the fraction of signal and background, which is the same that ABCD gives you, no? ABCD gives you at the end, in region A, how much signal you have.
So how many parameters you have? Lambda, mu, sigma?
Yeah, you have 4 here and 3 here, 7. And the fractions 8. 9, because we have 3 classes.
So it's just one normal distribution?
It is.
One normal, right?
Yeah, it is one normal distribution for the 2 masses. You have a lambda if you have a exponential, right? So the 2 background BBCC and CCCC, those are exponential. And the beta function needs 2 parameters. So these are the 2 parameters of the beta functions, when it is C or when it is bottom. Okay? And we start with bias and we get the correct. Okay? And the question is, the question to compare ABCD versus this, it is the fraction, how you infer it better. And of course, if we made a paper, it's because we infer it better with Bayesian. But there are many reasons. Okay, this is for the 1%, 0.5%, and 0.5% signal here. I don't remember still which is which. Okay, here it is 1% and 0.5%. Okay, and Bayesian infers much better than ABCD, because in ABCD, when you have some part of your signal that goes to the other, to the control region, you end up making bad estimations. But, I mean, this is a result, but at the toy model level. We are working at the toy model level. But let's see the experiment again. You were involved in this one?
No, not in this one.
This is the data and the signal and simulation, no? So this is in some invariant masses of the 2 Higgs candidates. And this is what how they define a control region. And they have to define it in such a way that they don't have too much background, because background is huge, no? Well, and the first thing to observe, if you do a counting around here, you are missing about 10–15% of signal, which you say is not that much, okay, but these are like €1 billion approximately. But the more important thing, they use a B tag of 0.77 because they need to suppress all the QCD background because of S over the square root of B. Okay? But here, the probability of having, 4 bit tags, it's 1 minus 0.724, so you are missing 65% of the events. 10 million euros, 10 billion euros. Okay, you are missing it because, okay, I'm going to try to convince you that S over square root of B, it is something that has to do with how we used to do analysis. You can recognize things that have S over square root of B much less than 1 and 10 to the minus 4 if you have the sufficient multidimensional space to see the data. Because when you say S over square root of B, at the end you are doing a number versus a number. You are a multidimensional reducing to one dimension. So it is not hard to imagine a setup where if you see in one dimension, you don't see anything, but if you see in other dimensions, you do see a correlation or whatever that. Okay, so now we go for this. Okay? Exploitation of continuity and unimodality. This is prior knowledge, and most of the physical distributions are continuous and most unimodal. So this is what the bit-tagging score distributions for TT bar, TT bar sample. So you expect that TT bar, this is quite like this. This is a neural network that, that makes whatever way and gives you this score. Now, when you are in die-Higgs, you expect this not to be this, but you expect them to be about the same thing. Eventually not that good, but let's say that you have some prior, and we're going to forget about jet and only think about charm and bottom. So previous work, we did this approximation. Now we're going to infer the continuous and arbitrary distribution. And this is a challenge, no? How are we going to do it? Yeah? Without cheating. We're going to exploit the continuity, the unimodality, and the multidimensionality of the problem. You have 4 bit-tagging scores. And you know that they are either for bottom, for charm, 2 and 2. So the first thing is Gaussian processes. That, as you may know, you can approximate, you can sample continuous curves using Gaussian processes with a covariant matrix that has the off-diagonal terms going to 0, so the bins which are next to each other have more probability of being correlated, and you cannot have, yes?
For Gaussian process, there is always something I've always been puzzled about. I mean, the magic around the covariant matrix.
Yeah.
How do you choose it?
Well, you model it, good. But you use your prior knowledge. You use your prior knowledge. What prior knowledge you use? You have some expectation of how continuous you expect this curve to be. No? If you, that has to do with the number that is in the off diagonal. And that's it. And you can, if you have some prior knowledge that you expect here to be less smooth than here, you can model your covariant matrix to have a smaller number in the some part of the off diagonal, how it goes to 0. Okay?
Yeah, but it's mostly empirical, no?
Yeah, but recall that these samples curves, even if you change this, you still are going to be able to sample the same curves, but different probability. And then the data will do the part to find the curve that best fits the data. There is some, of course, that there is some dependence on your prior information on the results, because there is always that. There is no intrinsic information in the data. Okay? And that is a part of the covariance matrix. Yeah. But let's buy this and go to the next one. The next one is going to be unimodality. So this is a PDF in 20, 30 dimensional space where you want to bin your curve to make it bin. Okay? It could be made continuous, but it would not be useful for the next one. So this is the covariant matrix. You put something around here that you do it by eye, you sample, and you see how continuous they are. Right? If these numbers go to 0 very fast, the thing is not continuous. Okay? It has to do with your expectation, but it's not defining you what your curve is going to be. It's just giving you different probability on different curves, and now the data will do the rest. Okay? So this is a way of sampling continuous curves around a central curve with very few hyperparameters. No? So this is the prior information, it is continuous. And we know that we're going to have 4 from here, or 2 and 2, and in addition that these distributions are continuous. So the game is with these priors. So the dot dash is the true distribution. The dotted, it is our prior mean, which, as you can see, it is biased from the true one. Okay, and as you can see here, this sampling allows you to reach to the true one without any problem. Okay, so the game is to start with biased prior, and the data will shift the posterior to the most likely distribution, which should be the true. And we are leveraging multidimensionality, continuity, and that this is a cheat. For bottom, for C, to C to B and for C, it is good, but it doesn't take into account some detail that at the LHC beyond eta 2.5, you cannot put a tag to the jets. From now on, we are neglecting that. We are working on that. So, I don't know if have you seen, if you, we have 3 classes. If you have 3 classes, you have 3 numbers that add to 1. 3 numbers that add to 1, the way to plot them is in this simplex, a 2-dimensional triangle. So here it is the true fraction of events. And as you see, 100 events, you have a posterior that is not working that well. When you see 250, it's getting better. When you get 500 events, well, you get a good prediction, a good estimation of which is the fraction of each one of the classes. And you have retrieved the correct distributions. Actually, all the parameters are useful. There are not nuisance parameters. Correlation, 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 okay? But this is one of the tools where now we are not using the betas. We are inferring the arbitrary distribution, and the key is that, well, all are keys. The key is that you have 4 events, 4 beta scores, and you know they are 2, 2 and 2, or 4 and 4, and you know they are continuous. Now I'm going to go to a second way of doing this, that this is unimodal model. Let us assume that the distribution, whatever it be, it is unimodal, that this is distribution. Okay, the neural network maybe doesn't have why to be unimodal, it might have an error. But if you say about the impact parameter of the B jets, and yes, they are unimodal. And many experimentalists have told me that to some point these neural networks have such an improvement, but such a large systematic uncertainties, that at some point, no, it's not clear whether by using physical magnitudes like impact parameter or things like that could reach a better agreement. So now the question is how we can sample unimodal arbitrary continuous curves. And here comes the co-author, who is a mathematician, who had the idea. So this is prior information, unimodal and continuous, and it works like this. This is very nice. How to construct unimodal arbitrary curves. If you have 20, 30 bins, it is easy to construct a curve that have the maximum in the first bin, the second, the third, no? Just linear. You are add one, and subtract one, subtract one. Now, instead of adding 1 and 1 at each bin, add a number sample from a half normal. This is the orange curve. So you add 2 times and subtract 18 times. Add 3 times and subtract 17 times. So you will have things that are unimodal, because they can have only one mode. They are continuous, because you are moving in a bin. You control how continuous they are with the sigma of this. And they are unimodal. They do not integrate to 1. So to have them integrate to 1, what you do, you apply this softmax that essentially is dividing by all the bins. Now, if you see the orange, you have arbitrary unimodal curves, but they have the maximum in 1 exact bin. So one way to do it would be to choose 1 at random of the 15. And it is unimodal at any place. But something more clever, it is to do a sum of the orange curves weighted by numbers that add to 1, but you have more probability of having only 1 large. How you construct n numbers that add to 1, and it is likely that only 1 is large, with the Dirichlet distribution. Okay? Sum orange curve weighted by a Dirichlet distribution with a small parameter. For those, I mean, I have heard of Dirichlet distributions in very recent times. It is something physicists not learn, but Dirichlet it's a distribution that samples multinomials, samples numbers that up to 1. And you can control, you can play with the parameters, so these numbers are all approximately equal, or they are all very small except 1. It has to do with in what part of the simplex it has the mass, the distribution. So this is so fun that I can sample like this, many unimodal distribution. So now we can move in a space of unimodal distributions. So we can do the same game, but we are asking that the key ingredients are unimodal. So now our prior, these are the true, and our prior, we only ask their unimodal. And we go with that, and we go again. These are the prior, these are true, this is how we begin. And when we do 100 events, we start to get a good guessing, and a better guessing.
Let me just understand these steps. So every time you put a new event, you update your prior to make it match with result.
Yes. Or you do it all simultaneously. It's the same thing. Yes.
Okay.
It's the same thing.
I still don't understand how you go from the first to the second one. What are you doing to update your priors exactly?
Sorry?
How do you update your priors to get the final?
Well, as far as you can write this, you can let the machine find the other one. And this is easy to write.
I understand. If you calculate cross-sections, I know how to write that. But you're saying you're not doing it.
No. So you have to think about a graphical model where you know that the class is either 4 bottoms, 2 charms, 2 bottoms, or 4 charms.
And that allows you to write that without
Yes.
any knowledge of quantum field theory.
Yes, totally. Because you have, what you're measuring is 4 bit-tagging score. Your data are 4 numbers. And your model is that these 4 numbers are either sampled from 4 bottom, from this unimodal, or from this, or 2 and 2. Pure mathematics, yeah. Okay? And it works. Okay, and the thing is, well, correlation plus unimodality knowledge. Okay? So one could access to much of the data that we are not studying now. Okay? Of course, you're going to have much more for jets, much more QCD background, thinking about the Higgs. Okay, that has to be studied. But do you believe me, no, that that's very important? But do you believe me that S over square root of B is something too simple?
I'll ask the question later.
Yeah, okay. But do you believe, no, that S over square root of B, I can write you a very easily some distribution that if you just see one dimension, say, okay, you don't see, there's no way to see it. But if you see the second dimension, so it's a matter of being able to see in many dimensions, which powers you, okay? S over square root of B is counting experiment. Well, so nothing, we have performed, well, we have done many calculations, many simulations, no, to see that everything makes sense, like with different seeds, always, that is a robust result, that is not just chance, okay? That you have a better, as you have more events, you approach the true, and you have more probability on the true. And this is about the fractions. Everything improves as you go, as you put more events. You have here like different models, like Dirichlet, Gaussian process, and unimodal. The unimodal thing, the good thing is that it works in 2 minutes, and the Gaussian process takes like 20 hours. And the reason is because sampling, we are here in something like a 50-dimensional space because of the number of bins. So sampling Gaussian with that number of bins is complicated. So outlook and conclusions. Right. The Bayesian framework generalizes and improves ABCD method, that's for sure. Okay, ABCD is something great, fantastic, from 1997, first paper, but it has to do with adding and subtracting. Okay, we can see the shape of the curves and get more things. Okay, it serves to exploit multidimensionality. We have seen a very toy model that improves this. No, this is the problem. Then we have improved it with the arbitrary curves, and we have seen that also works, but here we are not using the masses, we are just the flavor. We are putting building blocks into our main chimera that it's HH to 4 bottom. Okay, we are extracting correct distributional fraction, we are using very few assumptions. We reduce the simulation impact, of course, and we are increasing the modeling impact. There is a model going on here. That's a problem that has to explore. I mean, the final paper it is to do the same thing with a neural network, train your neural network with the biased data, and see what you have, and then the same thing with the biased data, do the Bayesian analysis, and see how close you improve. So that would be at some point we will do that paper. Well, and this works. It is robust. And nothing. It is nice to observe that the die-Higgs production for 2035, 2040, it is expected to be very close to the discovery yield of 5 sigma. So any improvement in this direction, it is always very welcome. One might have some doubt about the experimentalist, how they every time know better the detector, but they will end up measuring it, okay? And nothing. We have many things to do, okay? Integrate all the steps in unique base, analyze systematics, analyze more background, okay? BB gamma, so we have up to 2035 to do this. But essentially, Bayesian tool looks promising. No haircut, no signal, and background region, no hard assignment. That is something that one has to know every time one you do it. You want to take a few days to think if you can avoid the tagging, if you can avoid the hard selection. If there is a clever way to include the shape of the curve, because it gives you a lot of power, no? Go analytic and probabilistic, no? We can do ABCDs, you feel very safe because you are doing multiplying and subtracting. But come on, the other is just derivatives. Huh? Multidimensionality, correlation, and this, no? There is more info in the data than what is currently being used. Yes, I am certainly that, yes. But of course, that we do know that it is very hard, and experimentalists are doing a great effort to improve the analysis as data comes in. Okay, and that's very hard, I can imagine. Okay, and we are trying to improve this sensitivity. But essentially, if you think a little bit, this changes the S over square root B thinking. Okay, you can have, because you can have one region where you have much more background than signal and still get the signal. It's not a counting experiment, it's a shape experiment, a derivative analytic. Okay? Well, essentially this, no? We are trying to push the information frontier using the Bayes theorem. Thank you very much.
So first, thanks for the talk. As you may have gleaned, yes, and I'm an experimentalist from LHC from CMS. I have 3 comments. First, let me preface everything saying that I like this and I agree that we should go beyond the ABCD method, of course. And that's why I'm going to try to poke the holes, okay?
Yeah, I love it.
First, I think it's, I agree that we have to explore the shapes and the correlations and we should avoid hard cuts where possible. But you said yourself, the big cheat is that you are comparing with 4Bs with BBCC and CCCC. You are, of course we have to get rid of the QCD. I have to get rid of the QCD at the trigger level. Or conversely, putting 10%, 1%, 0.1%
yes.
signal in the background, come on, that's peanuts. Do it again with 10 to the minus 7 and come back and tell us something. And then I can start believing you. Find 1% we can do it with our eyes closed. The second thing is, how does this actually work if you have nuisance parameters? And again, I'm not talking 3 nuisance parameters. I'm talking 300. I have to deal with 300 nuisance parameters. If you can do all these calculations, if any of these survives the 300 parameters, I'm ready to try. And the third criticism is that I agree with you, S over square root of B is not the be-all end-all. But it's not me who you have to convince, it's the editor of nature physics. And the editor of nature physics will ask me, okay, given what's the probability, and that's one number, what's the probability of these results you're observing not being a statistical fluctuation? I want this to be a statistical fluctuation less than 1 in whatever millions. And then I have to answer that guy. How does of course, we can wait for the editor of Nature Physics to retire and somebody with a more open-minded to join, but I have to actually publish the Higgs discovery. What do I do?
Okay, let's go one by one.
Sure.
One by one. The first one was about 10 to the minus 7.
Yeah.
Yes, we are working on that. We're working on that. Because, let me plot here a little bit. The reason why they choose the curves are like this, no? From B and for jet. If you do the cut around here, this has 0.77 of efficiency. That's what they're using. So I wonder if can we do this. Okay? That, of course, gives you 10 to the minus 7, 10 to the minus 8, actually. Okay? What we're going to, I think that we can do it, because the machine does realize that it's full of background. The problem is that we don't have a machine that can compute to have 10 to the minus, a ratio of 10 to the minus 8 with 3,000 BB bar 4B event what we expect. Then you need 3 times 10 to 3 times 10 to 11 events. So my machine cannot evaluate inference on 10 to 11. What we're going to do is going to move to here. Okay? Up to where we can move, and that's going to be, I don't know, 10 to the minus 5, 4, 10 to the minus 5. And we're going to show that these results are doable, and that even though S over square root of B can be 10 to the minus 4, 10 to the minus 5, you do have an estimation, okay? And about the third thing, you will have an uncertainty. Okay, you will have an uncertainty, and we have to do it with zero signal and with non-zero signal, and be able to recognize both of them. And about the 300 nuisance parameters, I'm going to be sincere. I don't know what is a nuisance parameter. A parameter for a Bayesian never is nuisance, always is useful. Okay, but I think that, for instance, having the shape of the curve J is what usually called nuisance, because you don't use it for the result. And we are, in this case, we are having 25. We are making 25 bins, so we have 25 nuisance parameter. We can have 300. Believe me, these guys, there is something that we have to understand. The statistician guys who are doing these things for neural networks, for social networks, for whatever, they don't do physics, they're incredibly clever. And the data analysis that we do, I am starting to learn what they do, and I do realize that what we are doing, that we believe to be very clever, is very basic and full of missed profits. So that is what I'm trying to learn. And to these guys have an abstract thinking, a way of doing things, techniques, and numerical techniques to find maximums that are so good that I think that we are beyond them, below them, and we should try to catch up instead of having the nature guy since 20 years ago saying, "No, we're going to use the p-value." Okay, yeah. But that's something that, I mean, the guys who at the beginning of LHC decided to do this kind of statistics, they were very correct, because of course at that time it was the best thing to do, and I agree with that. When you start to see this development started mainly, I would say 2003. 2003 with LDA, which is the latent direct allocation, that made an exploitation of how to use Bayesian inference to extract the topics in the Wikipedia. And from then on, it has been a development that things have improved so much. We, in the high energy physics community, are still using some statistics. It's like going from here to Buenos Aires through China. We are doing a huge profile likelihood. We don't use priors. We say, no, we can experiment, no, we can You are biasing your result with the prior, but we use profile likelihood. Okay? And this thing, I think that the community deserves a talk about this. And as you said, there are some pyramidal construction that has to be. Sorry.
I'll defend the editor a little bit, right? Because the way this is designed, right, is to avoid false positives. Right? That's why we have
Yeah.
this signal for background starting to background of 5, right? I have seen 5 sigma signals go.
The Opera experiment.
Yeah.
And it was 5 sigma, see with your eyes signal. It went away because we're looking too many distributions at the same time. That's the problem, right? You get a 5 sigma if you ever only, famous Lucas were that, right?
Yeah.
If you only ever look at one distribution and you see something,
Yeah.
that's really 5 sigma, but if you look at all possible distributions
Of course.
everywhere, right? And is there a way to estimate the false positive error you're risking when you do something like that? Because that's
Yeah, of course there is a way. The way they ask question is if there is not an infallible way.
Yeah,
There is no such a thing.
Maximize.
Yeah.
Right? You know how to do these things with the measure. Yeah, you have this measure, right? That's the way.
You have this?
You have this measure when you do
Yeah.
the usual frequentist thing, right?
Yeah, yeah.
You kind of know what's the chance this is a false positive.
Yeah.
I don't know if that's easily assessed.
Yeah, I mean, it's part of the whole statistical analysis. I mean, to have the probability that you do, I mean, depending on the hypothesis you put, okay, but that's part of the whole probabilistic analysis, no? I mean, it is the very basic thing, no?
But
Yeah.
That's the trade you're making, right? So when people throw away 65% of the signal, like we said, right? They're doing that to avoid false positives. Right? And then if you allow for more of the signal to come in, you have to at some point present a plot where you show how much you're paying in terms of the chance of seeing stuff that is not there.
Yes.
Trade that needs to be put in quantitative terms, right?
Yeah.
Because then you can judge what is the best analysis.
Yeah.
At one point, to actually say a new particle has been found or a new process has been found, people will always, at the end, right? You can use something like that to actually see we're starting to see something, but in the end, to convince people I discover the signal, that needs to be put in very quantitative terms, right? That you're saying, well, I have more power now because I'm looking at the shape of the curve, but I didn't increase my error probability.
Yes.
If you do that, then it's clearly better, right?
Yes. I agree with you. We haven't gone in detail with that, but I can tell you that the statisticians are much more robust than what we are. And no, because it is no. No, it's not a matter of conservative. Doing the things correct. It's not a matter of being conservative. It's doing the things correct. You're being conservative to the potential errors you can do. But the thing is to do the things correctly. No? And much of the, I mean, we are not reading the statisticians' papers. We really believe that we have the chapter 32 of the PDG, and we go there. That was written in 1997. That chapter has not changed since 1997. Come on, man. I use statistics. Statistics has evolved incredibly. You can see it not only with ChatGPT, but that blows up your mind. But that statistics has evolved incredibly. So many smart people there doing things, theory, numerical analysis, computational power. And we are with 1997 PDG chapter 32.
At least now we hire some statisticians to work with us.
Lion's book.
Lion's book.
Do you trust them? Do you hire them and then you ignore them?
The guys from Duke. Yeah? Yeah.
I
Yeah. It was great to talk to you. Yeah.
He's in the first floor, room 114, and he knows where you are.
Is that a fact?
Very good.
That's